So welcome everyone on the first Quantum Research Seminar Toronto. So first of all, sorry for all the technical issues that we had. I hope it will all work well from now on. So QRST is, like, briefly let me tell you about the initiative that we started here. So this is a series of meetings coordinated jointly by group of Alan Aspuruguzik and Zapata Computing. So we wanted it to be a monthly seminars in Toronto, but due to current circumstances, it's actually right now it's more like virtual Toronto, and we plan all to distribute them all through YouTube or other video platforms so that people can have access to that later on. We plan these talks to be pretty in-depth, research-oriented, and very, like content-heavy by people who really know what they are doing, people who are expert in quantum computing, and both from academic side and the industry side. The format will be 2 speakers per meeting, 1 meeting per month. We plan for it to roughly take about half an hour per speaker. So we would like to make it possible for all the participants to ask questions. And we decided that the best way to do that would be if you, after the speaker finished, if you want to ask a question, please raise your hand. There should be a button in Zoom which says raise hand. So once you do, then we'll say who can ask the question, and that person can unmute and ask their question. So if you have any problems, or if you have any suggestions for the future speakers or any feedback, please contact either Alba or me. Our emails are here. And well, without further ado, let me introduce you to the speakers. So today we'll have 2 talks. First one will be by Pierre-Luc, and it's called An Application Benchmark for Fermionic Quantum Simulations. And it is about the recent paper that we have published. So Pierre-Luc, just like briefly about Pierre-Luc, right now he works at Zapata Computing. He did his PhD in 2016. Afterwards, he joined Alan's group. He is working, so his research was mostly focused on materials for superconducting qubits, and also at Xanadu, he briefly worked at quantum machine learning. And yeah, I'm giving all the stage to Pierre-Luc. Okay, so Pierre-Luc, please share your screen.
All right, thanks, Michał. Is it working?
Yes, I can see that.
Can you see my presentation? Yes.
Yes.
Okay, perfect. So well, thank you for organizing the first quantum research seminar, Michał and Alba. So I did not expect that many people would join. I tried to prepare a talk, roughly like 25 minutes, to explain the latest paper we published at Zapata. So it's about using quantum simulation, so the variational quantum algorithm, to benchmark quantum processors for applications, for near-term applications. So like I'd like to mostly also thank my co-authors. So there's Michał, who participated in the research. There's Jérôme Gontier, there's Antoine Toussaint, Jonathan Romero, and Yudong Chao, who all participated, and made this research possible. If you want to have a deeper look in the research, there's the archive number of the paper. And yeah, let's start. So just introduction, like we know that noisy quantum NISC machine devices are becoming available. What is expected is that near-term applications will likely be simulation of quantum systems. It will be combinatorial optimization, probably also some machine learning. But we're still not yet at the point where those simulations will necessarily be like where we can have an advantage over classical methods. Not yet, but like we'd like to determine exactly when. And for that, what we came up is a form of benchmark, which is an application benchmark. Really in the perspective of trying to capture at which point in time we'll be able to do simulations which are beyond the power of classical computers. But benchmarking is absolutely not new in the field of quantum computation. There's different levels of benchmarking for different part of the quantum computing chain. At the level of hardware, there's already process tomography to determine the quality of single qubit gate. There's randomized benchmarking to study the noise in the basic unit, in the basic quantum gate. In the supremacy experiment, there's cross entropy. Cross entropy can be used to benchmark whether we're beyond supremacy. IBM has introduced also the notion of quantum volume, which is a more general form of benchmark closer to application, and it gives us it gives us numerical values that tell us like which size roughly of quantum circuit we can run with high probability of success. But these all these benchmark methods do not account specifically for the structure of the quantum circuits we use in specific applications. Also, they do not, for those applications, if we're going to benchmark the capability of quantum processors to execute algorithms beyond what we can simulate classically, we'll want a method which can scale to several tens to hundreds of qubits, which should be possible to build in the coming years. And for that purpose, what we introduce is the notion of fermionic length, which is built from a very specific, a very special model from condensed matter, namely the Fermi-Hubbard model. This benchmarking method is meant to be holistic in the sense that it will only yield a good score when there's low errors and low amount of decoherence in the quantum processor. When we have a scalable quantum architecture also, for VQE type applications, we'll need adequate parameterized quantum circuit to reach a good score, and like also effective training method. So like all the elements of the chain have to work perfectly to get a good score on the fermionic length benchmark. Before detailing exactly how it works, let me just introduce a bit the Fermi-Hubbard model for those who are not specialists. So the idea is that we have first, like the Fermi-Hubbard model is one of the simplest models that we have. It's a caricature of interacting electrons. So like it contains all the main ingredients to study electrons in solids. It starts from a tight binding description, and then it adds electron-electron interaction, which is assumed to be screened. So it's a local, so we add Coulomb interaction. And despite its simplicity, it's a very general model in the sense that it can describe many phenomena of correlated electron, like magnetic ordering, the metal-insulator transition. It can describe superconductivity. It can describe Pomer-Anshouk instabilities. Its ground state is not a mean field, meaning that like there's no general efficient classical calculation that can yield the ground state. And also a very interesting property is that there's few parameters, yet the dimensionality of the lattice will strongly influence on the computational complexity of the problem. So like in 1D, like if we have those orbitals, in 1D, the model is exactly solvable through the beta ansatz. Yet in 2D, it's not known exactly how to, there's no known closed form solution for 2D. And even worse, like if we assume there can be local magnetic field, then it's shown to be QMA hard. So there's no, it would take an exponentially long amount of time to solve even on a quantum computer for the full general 2D model. A bit more formally, the Hamiltonian we consider for the benchmark, we'll use the 1D model because it's of the property that its solution for an infinite chain is known. The form of the Hamiltonian is contains a hopping term between orbitals. It contains a local Coulomb repulsion, and it also contains a chemical potential, which controls the number of particles in the system. And as we said, it's the 1D Hubbard model has the very particular property that the infinite chain, so we know the exact value of the ground state energy, at least the density of the ground state energy for an infinite chain through the beta ansatz. And there's at half filling, there's even like a simple numerical integration that can be done as a function of the Coulomb interaction. That gives us what is the energy density as for different values of the parameter. And these values are easy to compute. So like in practice, like a strongly correlated, like a correlated model will be like for the finite value of the interaction energy. And also an interesting property that we use is that we know that the correction to the energy density follows 1 over the length of the chain. So for finite chain, the correction to the energy will scale inversely proportional to the size of the clusters that we're using. And we're going to use this fact to construct the benchmark. In practice, so this is known to be like this is typical for the experts. So like we'll use for the purpose of this problem, we'll use like a Jordan-Wigner encoding. And by choosing the appropriate Jordan-Wigner encoding of the Hamiltonian, we're able to encode the Hamiltonian with qubit operators, which act on at most on 2 qubits, like as we show at the bottom here, which makes the measurements on the quantum computer fairly easy to proceed, and like the number of groups of terms does not change as a function of the size of the chain, which is a very interesting property for the purpose of the benchmark. So how does the benchmark work? We assume we have a VQE problem. We have a quantum processor. We want to see, we try to minimize the energy of the chain, starting from a small chain with 2 sites. We do a VQE optimization. So we do a state preparation, which yields a ground state for some state for some set of parameter. We measure the energy. And using a classical optimizer, we try to minimize the energy of the chain we've prepared. So for like 1 by 2, we'll get some number. And if we keep going with the optimization, ideally, when we reach the ground state, the value of the minimal energy will converge as we increase the length of the chain toward infinity, toward the beta ansatz value, which is known analytically. And a very interesting property also of the 1D chain is that the number of measurements to estimate the energy density, not the energy itself, but the density with precision epsilon will scale inversely proportional to the length of the chain. So we won't need an increasing number of measurements up to a fixed accuracy to resolve the energy that we're trying to measure. But at some point, there's going to be noise, there's going to be decoherence in the quantum processor. And what we'll see is that we won't be able to reach, even given the large number of qubits, when we hit the noise, we won't be able to prepare an exact ground state. You can view, in some sense, the noise roughly as like a finite temperature limit. So like if there's too much noise, what we're going to be preparing is what we're going to be measuring is essentially the large temperature state of the 1D Hubbard model. And the optimal energy, the optimal experimental energy will diverge from the optimal 1/L behavior. And this optimal value is what we define as the fermionic length. So it's essentially the minimum value, the length of the chain at which we reach the minimum value of the energy. And this, since it's a rough model of quantum, well, there won't be a general benchmark for all type of fermionic simulations, but certainly for some types of material simulations, we know that preparing the ground state is not easy in general for the 1D Hubbard model. So it gives us an indication of roughly the size of the systems we can hope to try to prepare on a given quantum machine. And to be specific, so like one of the main motivation for this type of benchmark actually comes from the quantum supremacy experiment last year that came from Google on Sycamore. It's a breakthrough, it's a historical experiment where it has been shown that for a type of problem, namely sampling from random quantum circuit on this device, there's no efficient classical simulation that can also sample from the same distribution. And in principle, the experiment is scalable. So by adding more qubits, the distribution and improving the coherence and reducing the noise, the experiment is scalable. But in and out of itself, there's no real application. Maybe sampling from random numbers. Still, the physics of the device, namely like the form of the tunable couplers and the type of physics that emerged from that, gave us ideas that it may be possible to use this type of device to do fermionic quantum simulation. What I'll talk about is the connection, like what's the connection to fermionic physics. This goes through match gates, the theory of match gates and free fermions. And I'll quickly explain also what the form of the hardware efficient ansatz that we can define on such a processor. And then I'll show numerical results that where we estimate, do an estimate of the type of results we could get on the device. So the particular property of the architecture of Sycamore and namely G-bonds is that like the qubits, since they're using qubits whose energy can be tuned, they also have tunable couplers, and those tunable couplers allow the application by tuning the pulse, the area under the pulse of the tunable coupler, and also the detuning of the qubits. You can create a parameterized set of gates, and like it has been demonstrated experimentally also in another paper from Google, where the 2-qubit element, like the 2-qubit operators, qubit gate between as the form of like a parameterized I swap and a parameterized C phase. In practice, there's also residual phases, which are represented by the Z operations. And those devices also support single qubit X rotation and Z rotations. And this particular form is very, very interesting because it relates to the physics. It minimally connects to the physics of free fermions, and we go beyond and define that, define a non-Gaussian ansatz, fermionic ansatz from this physics. Just quickly, it's a quick theoretical digression. So like what are fermionic Gaussian states? it's useful to work with the Majorana operators, which are the quadratures of fermions. And for quadratic states, whose often coming from quadratic Hamiltonian using only like one body operators, the full state can be described by a covariant matrix, which can be measured. So it's essentially the one body reduced density matrix of a given state. And all operations on those states are efficient to compute classically. They can be described as they can be generated from quadratic fermionic Hamiltonians. And there's a nice connection, there's a nice easy way to compute Gaussian transformation. So given like a unitary implementation of a Gaussian transformation, it corresponds to a rotation in the space of like the fermionic operators. And that's how we efficiently compute like the Gaussian transformation and Gaussian ground states for free fermions on a classical computer. And this corresponds to all to the dynamics of free fermions. And interestingly, those transformation can be described by the theory of match gates. Match gates are 2-qubit gates which have the following form. So it's described by two matrices A and B, which are unitary 1-qubit operations whose determinants are the same. And when defined on a 1D array of qubits, they have all those operations can be described by the following generator. So like it's, they correspond essentially to all fermionic Gaussian transformations. So they're generated by XX, XY, YX, YY, and single Z operation. And all those correspond to like terms which can appear, which are allowed to appear in quadratic fermionic Hamiltonians. What is known is that nearest neighbor match gates on the 1D chains of qubits are classically efficient to compute. Yet, as soon as we allow for non-nearest neighbor match gates, so if we do match gates on the 2D array or on any dimension, which is any array which is not one-dimensional, or if we have conditional phase, then we can construct all universal quantum circuit, which means that if we have like a sycamore array, if we were to take any one-dimensional array there and only limit ourselves to match gate operation, namely I swaps, which are a type of match gates, and single Z, then those simulations would be efficient to compute. Yet, if we add also layer like non-nearest neighbors, non-nearest neighbor match gates, like I swap across the chain that we pick, and C phase, then we get like a universal gate set. So an ansatz built from these 2-qubit elements from layers. So if you imagine that like you're gonna have like simultaneous layers, which are done as in the supremacy experiment to define an ansatz. So say the red layer, the yellow, then blue, then green, and then you repeat those layers. Then you get a very natural non-Gaussian ansatz. What's happening is that like the extreme points of these ansatz actually corresponds to the random circuits which are used in the supremacy experiment. So by construction, such an ansatz is not possible to efficiently sample classically. So we know we're preparing states which are difficult to study classically, which is exactly what we want out of quantum simulations. One subtlety that arises like when encoding quantum systems on such a lattice is that there's a lot of freedom in choosing like which qubit corresponds to which orbital, and we limit ourselves here to three types of ordering. So namely like an interleaved ordering, which we think could be useful for like the 3D models of Hubbard. And also study like an horizontal layout where the qubits are like where the spin orbitals are ordered like horizontally in the vertical ordering. mostly because we think like they work well with the 1D system. And to try to test if our ansatz work, if like our method, like if our methods work, we coded this up in Orchestra, so our the Zapata platform, which is based on workflows, and we tried to converge it and measure what is the maximum length we could get, assuming that we have some kind of bounded depth system. So we assume bounded depth ansatz. So it's like the spherical cow, if you want, of decoherence model. You just assume that there's a cutoff in the maximum depth you can reach, and we try to see like what was the maximum length. So like roughly speaking, what we get is that we get the Hamiltonians, we get the number of operators, and then the workflow proceeds. They build the ansatz, we generate parameters, and then we do a layer by layer optimization of the energy, and we increase the chain. Depending like on the optimization path on the initial parameter, there's always some variation in the final in the final energy. So that's why we can do several runs and we can pick the optimal value. Of course, there's always improvement that can be done on the training, and it's also part of the benchmark itself. So as we increase chain length, we can start with, we have the different orderings, and we increase the number of layers. We can start with like length 2, then increase to 4, 6, and 8. And what we get is essentially that like the length 2 is easy to prepare on those, like independent of the ordering, and the ordering here did not have much influence on the length itself. But like we clearly saw that like after a maximum number of layers, like we could not prepare, like the ansatz was not deep enough to prepare like a chain of size 8, so which uses 16 qubits. Like in practice, what it would mean is that we would need to reduce the noise, reduce the errors to increase the depth to be able to prepare like the ground state of the chain 8. So like assuming like so some finite depth with which we roughly estimate from the quantum supremacy paper, we think like order chain of length 6 using 12 qubits could be doable like on the Sycamore processor. And just quickly to finish, so like this is for the very specific case of the 1D chain. In principle, what we want to do is start from like for real system, we'll want to do something like a bit smarter. So what we'll do is like we also came up with a scheme where we can do orbital rotation. Since orbital rotations are efficient to do classically, we do them on a classical processor. So we can vary like the terms of the Hamiltonian and have like a second order variational method, which makes sure that we can never prepare a state on the quantum processor which has a higher energy than the mean field state. So we're placing like a threshold, like we're pushing the floor of what we can do quantumly, at least as good as what we can do classically. And we derive like the exact formula for the method, and like there's also like the quasi-Newton method should be possible also from that. And this was all done like on the platform that we are building, so on Orchestra, which allows to study many parameters with many noise models, all in parallel and all automatically. It works wonderfully. And that's it. So that's thanks for the attention, and like I invite you to read the paper. And really like the main two messages are that we think that like fermionic length can be used to benchmark the quantum simulation capability of devices. And also we propose like potential applications to study like strongly correlated systems on devices with tunable couplers like Sycamore. And that's it. I think that's my time.
Great. Thank you very much, Pierre-Luc. So now, if anyone has questions, please raise your hand. It's like and we'll see that on the Zoom participant list, and then like unmute you so you can ask the question. I don't see any questions.
Questions?
Okay. So Matthias, I'm unmuting you.
Hey, thanks, Pierre-Luc, for the talk. So I had one question about this. So you're basically subtracting the infinite scaling density of the beta ansatz, right? So what can you say about the accuracy you need from a machine to subtract two numbers and then get a 1/L accuracy on the remainder? And can you track that? Can you, like, if you see the beryllium hydride plots of IBM, for instance, there's no way you will see a 1/L effect there. So can you realistically expect machines to have sufficient accuracy and energy to be able to take differences and then still see a 1/L?
Yeah, it's 1/L. So like, of course, in practice, like for very long chains, the corrections will like.
Well, it's not only 1/L, right? It's 1/L in the difference.
It's 1/L in the difference. Well, between the exact value. So you want to resolve like that. This
in the remainder. So you, like, if your computer is accurate up to 6 digits, that will, like, the most of the mass of that will be in getting the beta density right.
But those numbers are order 1 anyway. So like the what you're looking for, like the reference energy is order 1. So like really the difference is going to be like order of 1/L. It's really what we're going to try to resolve. So like if it okay, it's not really between different chains, because like what you're going to see is that it's going to converge very like it's going to converge towards some number, and as soon as you hit too much decoherence, like there's going to be like an exponential wall that you're going to see. So like there won't be too much ambiguity, like what's the optimal length of the chain that you get, well, at least like for bounded depth model. And also in practice, like the exact number, like it doesn't mean that like it doesn't translate perfectly to all other systems. It gives you an indication of the types of like the order of magnitude of the number of orbitals that you can expect to simulate. So say like you want like it's not going to be like you're not going to look for a difference between say 12 and 14. You're going to look for a difference between say 10 and 50. At least for near term, because like if the control, like it also like for our numerics, we assume a bounded depth model. In practice, the real depth you're going to be able to reach depends strongly on the type of errors that you have in your system. If the errors are mainly coherent and the variational method mitigate a lot of those errors, so like if the crosstalks are coherent and like just variationally you're canceling a lot of those crosstalks, then like the depth that you get can be much greater than what you're estimating from say cross entropy benchmark. And it's actually to capture this these types of effect that we designed this benchmark, because it's not exactly clear without having the exact error model, which for a very large system you won't really have to know what are the real capacity of like variational methods on those machines.
Okay, thank you.